Hello, my name is Robert Overholt, and this is my extra credit presentation for Dr. Greco's Physics 2212 class. I'm going to discuss a little bit about Alan M. Nathan from University of Illinois and his lecture on the physics of baseball. So a little overview, he went over two major topics, the actual hitting and the ball-to-bat collisions, which include the physics of a bat, the action-reaction principle, and wood versus aluminum bats, as well as the in-air behavior of the baseball and how drag, lift, and certain spin impact the flight of the ball while it's being thrown or hit, and how that can be incorporated to make some really effective fancy pitches. So to start off with batting, the ideal hit kind of effectively utilizes a sweet spot. So with that sweet spot, the vibrations of the bat are minimized. The coefficient of restitution, which I'll touch on a little later, which is a constant with the baseball, and the batted ball speed, or BBS, is maximized. But it's important to know that even with an ideal hit, there's a lot of energy that's lost due to deformation, as you can see from that picture where the ball is greatly deformed upon impact. A lot of energy is lost. In a not so ideal hit, when the ball will hit the bat too close to the hand, too close to the location of the hands, then that results in a broken bat. Obviously that would not occur with a metal bat, but in the major leagues when velocity and swing speed are very high, this can happen quite often with wooden bats. As I mentioned before, the batted ball speed incorporates the pitch speed, the bat speed, and the collision efficiency, which is the constant Q. And that's the formula that was presented. And it's important to note that the velocity of the bat, similar to a golf swing and swing speed of a golf club, that the velocity of the bat is the most important factor, because each mile per hour of the bat contributes to about 6 feet of flight. On the contrary, the velocity of the ball contributes only 1 foot per mile per hour. The coefficient of restitution is what people may call the bounciness of the ball, or how much energy is lost during the hit. It's important to include this when you're determining the efficiency of a collision. As you can see, different balls have different coefficients of restitution. Now, in terms of the movement of the baseball, there are certain forces that affect the flight of the ball while it's in the air. The first is drag. Drag slows the ball down. As you can see in the diagram, right there, the drag force is going to be a resistive force, whereas magnus and gravity deflect the linear trajectory of the ball. So if it's going at a constant velocity, the gravity will pull it down, and the magnus is normal to the direction of the velocity. Now, these can be incorporated when coming up with good new pitches, such as the fastball, the curveball, the slider, and the screwball. Now, different angles of spin are induced on the ball by the pitcher's fingering position, which can be used to make good, effective pitches. Here's a more quantitative way of pitch speed versus spin deflective angle. So this lecture by Dr. Allen made me very interested on the effect of a cork bat. And you hear all the controversy, especially with Sammy Sosa, with what happens when the bat is corked. Well, when the bat is corked, it transfers less energy to the ball. Therefore, the ball will rebound faster and go farther off the bat. Another important factor of a corked bat is you don't lose much strength of the bat, but it's a lot less dense. So you can keep swing speeds from, or you increase your swing speed, and less energy is transferred from the bat. Thank you for watching. I hope you learned something from this lecture. Thanks.